revision part, then after that we will solve the more questions. Okay, so now we discuss the sequential circuit. Okay, so basically the sequential circuit is what? That is synchronized. Okay, synchronized, and synchronized with whom? Clock signal. That is, we can say that this is the reference signal. The reference. Now, in this sequential circuit, initially we go with the flip flops. Okay, with the flip flops, we can design a resistor or a counter. Okay, and last one we go with the FSM, finite state machine. Okay, so flip flop, the basic element of the flip flop is the latch. Latch. Okay, the basic element is flip flop is latch. Why it is called the basic element? Because latch is the level trigger. Level triggered sequential. The problem with the level triggered sequential circuit is that if we have this clock cycle, or any device that is trigger on a positive level. So basically the duration to trigger at this one. Okay, like similar to the run. Okay, similar to the running. If we go with the running, if the running is not started at the same time, so we can say that it is not possible to uh, we can say that if any person who is going to start late, there is chances that he will be not win that particular race. So what we do is that in the case of sequential circuit, like if 4 or 5 devices are working on that one, so every devices will be like these are the 6 devices. So one device will be start at this time, one device 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 at this time, and one device at this time. So every device will starting time is the different. So how we can say that these are the synchronized? Okay. So it is not possible that we can synchronize all the devices at the same time. But somehow it is a condition that these particularly all 6 devices are synchronized in this duration. It is not considered that this device, any device will be start here, any device will be start here, any device. Okay, so the devices that are not as synchronized now, it will be synchronized for a duration. Okay, for a duration. So that's why we can say that we are somehow synchronize these devices, that these devices will work in a duration of that. Okay, so that's why it is called the latch. The second thing with the latch, second problem with the latch is that if we design this latch with the NAND gate and NOR gate, the output is different. Output is different. Okay, this is the problem with the latch. So to overcome this problem, we go to the flip flop The flip flop is as triggered. The flip flop is the as triggered. This one or this one. There are two particularly edges are there considered. One is the positive edge, where transition of clock from 0 to 1. Okay, and second is the negative edge, where transition of clock was from 1 to 0. Okay, so two types of as triggered flip flop are there. Now these flip flop are classified in four different categories. One is the SR flip flop, JK flip flop, T flip flop, or D flip flop. Okay. Generally, for the case of registers we use the D flip flop. We use D flip flop. SR is basically the set reset. That is one the best scientist of Johnson's. Third one is the toggle, and D is the delay. D is the delay. Now, with respect to this one, we can draw three types of table. One is the truth table, characteristics table, and excitation table. In the truth table, we only consider the terminals S and R, and with respect to we are getting the output. In the characteristics table, we consider that Qn is also the input. It is not exactly input, but somehow the Qn plus 1 is dependent on Qn. So that's why we consider Qn as an input. But it is not an input. And Qn plus 1 is the output. And excitation table that is drawn between Qn and Qn plus 1 as the input. And with respect to this one, what is the S and R conditions? We are getting the output. Okay. This excitation table is required for FSM circuit. Okay. That is required for mm, any arbitrary circuit. Okay. This characteristics table is required for implement excitation table. Okay, and that is the basic table. That is basic table. Okay, if we go with the SR, yeah. Any doubts?
The truth table is same as the function table, right?
Yeah, truth table is same as the function table.
Okay.
Okay, so if we say that SR is 0, 0, 0, 1, 1, 0, and 1, 1. Okay, in the 0, 1, what we are getting? 0. It is called the set position. Sorry, reset position. Because reset is 1, thus that's why it is called the reset position. It is a 1, that means it is called the set position. 1, 1, we are getting a Qn bar, and this 0, 0, we are getting a invalid state. Why it is an invalid state? Because Qn plus 1 is equal to Qn plus 1 bar, and that is not possible. Okay, both output will be the same. Okay. Now with respect to this one, if I draw the S and R 0 0, Qn is 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and 1 1 1. 1 1 1. Now 0 0 we are considering the invalid conditions. Okay. 0 1 we are getting a 0 always. Doesn't depend on the Qn. 1 0 we are getting a 1 as well. And 1 1 we are getting a invert of Qn. So if previous is 0, so we are getting 1. If the previous is 1, we are getting 0. Okay. Now 0 0 0 1 1 0 and 1 1. Okay. So in 0 0 one condition we are getting a SR value is 0 1. 1 0 this one and this one we are getting a 0 1 and 1 1. So that means cross 1. Now sorry, that is 1 0 cross. So cross 1. Now 1 1 condition this one. So we are getting a 1 0 and 0 1 this one and this one. Wait, wait. Yeah, this one and this one. So we are getting a 1. Check whether we are getting a. Oh, sorry. That SR00 is we are getting a no change. That is we are getting a QN. Sorry, sorry. And for 1 1 we are getting a invalid state. Okay, so 1 1 we are getting a output as a cross cross. And here we are getting a 0 0. So we are getting a 0 0 at this and this position. So S is 0 for both position, but R is 0 and 1. So it is a 0 cross. Okay. Now 0 1 this position. So it is a 1 0. Now 1 0 1 0 0 cross, and last 1 1 is 1 0. Mm, sorry, no change. So 0 0 is this one, and this one. Okay, so this is a 0 cross. 0 1 is this one. 1 0. 1 0 is this one. 0 1, and 1 1 is this and this one. So it is a cross shape. Okay. If you want to remember this one, so S is 0 1 0 cross. R is from this one 0 1 0 cross. 0 1 0 cross. 0 1 0 cross. Okay. Now similarly for the JK flip flop, the problem is with the SR flip flop is the invalid state. Okay, so we go with the JK flip flop. So JK Qn plus 1, JK Qn plus 1, Qn plus 1, J and K 0 0 0 1 1 0 1 1 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1 0 0 0 1 1 0 and 1 1. Okay, so JK 0 0 is Qn. This is 0 1. Here we are getting the Qn bar. Okay, so if 0 0 Qn plus 1 is Qn, so 0 1. If it is a 0 1, we are getting a 0. If it is a 1 0, we are getting a 1. If it is a 1 1, we are getting a Qn bar. So Qn is 0, so Qn plus 1 is 1. If Qn is 1, so Qn plus 1 is 0. Okay, now this is the 0 and this one is 0. J is 0 and K is 1. So it is a 0 plus. Second, this is the 0 1 and 0 1. J is 1, K is 0 and 1. So J is 1, K is changing, so 0 1. It is a 1 0 and 1 0. So J is 0 and 1, K is 1. So it is a cross 1. And last one is a 1 1. So J is changes and K is 0. Now it is again similar 0 1 cross cross 0 1 cross cross. Okay. Now similar, we have a T flip flop. So in the T only one input is there. When t is 0, it is qn. When t is 1, it is a qn bar. So if t is 0, qn. When t is 1, qn bar. Okay. So it is a 0 0. We are getting t0. It is a 0 1. We are getting 1 1 0. We are getting a 1, and 1 1. We are getting a 0. And last is the D flip flop. D qn plus 1. D qn plus 1. qn plus 1. D. So D is 0. Qn is 0. D is 1. Qn is 1. So D is 0 doesn't mean what is Qn. Qn plus 1 is 0. D is 1 doesn't mean Qn. Qn plus 1 is 1. Now if it is a 0 0, we are getting a 0. If it is a 0 1, we are getting a 1. If it is a 1 0, we are getting a 0. And if it is a 1 1, we are getting a. Okay, so this is the tables. Now this excitation table, when we change one flip flop into the another flip flop, when we use the FSM model, so in this particular scenario we are using this excitation table. Okay, now the register part. Now the register part is that it is a four types of register are available. One is the SISO, SIPO, PISO, and PIPO. If we have a three registers, okay, the output QN is connected to the next input D. The output of Qn is connected to the next input D. And here we are getting the output D. Okay, so like for example, if we want 1010 data, so initially 0 is insert. Okay, in the first clock cycle, D comes here. In the second clock cycle, D comes here. In the third clock cycle, D comes here. Okay, now in the first clock cycle when D comes here, in the second clock cycle this one applied to this one, and this, sorry, 0, because initially we insert the 0. In the next second clock cycle, this 1 is applied. Okay, so 1 is applied here. So say after second clock cycle, it becomes 1. It becomes 0. Okay, here, and any invalid condition. Any invalid condition. When we apply the third clock cycle, so this 0 comes here, this 1 comes here, and this 0 comes here. So we are getting a 0, 1, and 0. Okay, so after three clock cycle you are getting the output. So that's why it is called the serially, because every clock cycle the data will be shifted a one time. Okay, so that means if you have a three flip flop, you have a 3-bit flip flop, so you required a three clock cycle to get the output. Okay, now in the case of parallel out, we are taking output here. We are taking output here. So initially in the first clock cycle, this 0 will be goes into this one. Okay, so you are getting a 0 here. Doesn't mean what is the output, it is a don't care, because it is not a correct output. In the second clock cycle, this 0 goes to here, and this 1 goes to here. So 1 is coming, Here 0 is coming here and it is a don't care. In the third clock cycle, this 0 goes to here, so we are getting a 0 here. If 1 that is coming from here to here, so we are getting a 1 here. This 0 we are inserting in the third clock cycle, so this 0 will be go here, so it is a 0. So we can say that every clock cycle we are getting the data. So it is called the serial in parallel out. Data is transmitting serially, but we are getting the output as a parallel. So it is called the SIPO. Okay. Now the question that is coming from that is coming, like for example, we are having this data. One, two, three, four. Okay. Like we are assuming the data 0, 1, 1, 0. Okay, so at clock 0, you are getting a data 0, 1, 1, 0. Now calculate what is the data after 6 clock. Okay, so if you are getting here, so 1, 0, you are getting 1 here. This 1 and 0, you are getting 1 here. So MSB is the 1 and remaining data is shifted 0, 1, 1. Okay, now these two is XORing is 0, 0 XORing with 1 is 1. So 1 here, now next data will be shifted. 0, 1 XORing 1 and 1 is XORing with 1 is 0. 0, 1 XORing is 1, 1 XOR with 0 is 1. Okay, 1, 1 XORing is with 1, 0, 0 XORing with 1 is 1. 0, 1 XORing 1, 1 XORing with 1 is 0. So 0, 1, 1, 0. So this is the data. Okay, this is the first question. The second question is that if we apply a clock signal of a 100, sorry, 90 megahertz frequency. If we apply a clock signal of 90 megahertz frequency, what is the clock frequency of output signal? What is the clock frequency of output signal? So any idea how we calculate the clock frequency? So with the output, you can see that this clock is 0. Now the data will be repeat after the 3 clock pulse, at 3 clock pulse. Okay, so what is the clock frequency of this one is f divided by 3. Okay, so what is the clock frequency of the output signal is 90 by 3 is 30 megahertz.
So here, hello.
Yes.
So here we need to identify the pattern there, no? Input and
Yeah,
output.
we have to identify the pattern
Then only we can
frequency.
frequency.
Yeah.
It's not depend upon how many beats are you're performing and all that.
No, not dependent on how many bits. At what how much clock is required to repeat the pattern.
Okay.
Okay, so if we
Okay.
required a 3 clock pulse to repeat the pattern, so that is the frequency is divided by 3 times
Okay.
because time period is increases.
Right.
Okay, so frequency will be divided by 3. Okay, now the second question, this is the first question. Second question is related to the clock. Third question is that if I change this particularly 0101, I can use this and this one. Okay, so if the initial value is 0101 at a clock 0, you have to calculate the number of clock pulse to get the data is 1101. Okay, so you have to draw the particular output after every clock pulse. So when it is a clock 1, so 1 and 1 becomes 0. So 0010. At clock 2, the 0 and 0 become 0. So you are getting a 0001. At clock 3, you are getting a
So
0 and 1. So it is
voice not clear.
hello. Voice is not clear.
Like you're talking from long distance. Like that.
Hello.
Yeah, is it now?
Wait a minute. Now it's fine.
Yeah.
Okay. So at clock 1, this 1 and 1 becomes the XOR part. So it becomes 0. So 0 is in this side and remaining will be shifted. Okay. Now again 0 and 0 is go to the input of the XOR. So it becomes a 0 and rest will be shifted. Now 0 and 1 will be the 1 and rest will be shifted.
So here we need to process up to until that desired pattern
Yeah,
will get
we are not getting the 1101.
right.
So clock 4 again 0 0, we are getting a 0 1 0 0. At clock 5 0 and 1 we are getting a 1, so 1 0 1 0. At clock 6 we are getting a 0 and 0 becomes 0 1 0 1. I think we are not getting a 1101. Okay, we are not getting a 1101. So I am taking the random question. Okay, so 1101 we are not getting because after 0 we again repeat to the 6. Okay, the same data is repeated.
Yeah,
Okay, if we go with the next clock, clock 7, we are getting the same data as
the
this one.
same pattern will repeat.
0 0 1 0
So we'll never get that pattern
1101. Yeah.
in this situation.
Yes, yes, yes. Okay, but this type of question may be given, maybe
Okay.
asking.
Okay. So currently we are solving question from the which mock test or random questions.
No. Which one?
Current questions you are solving from mock test or just random
This
question.
question. This question.
Mm-hmm.
That is taking. I am taking randomly, not
Okay.
mock. Okay, not
Okay.
related to any mock.
Okay.
Okay, we are not solving the mock right now. Okay. Similarly, if we are talking about the flip flops. Okay, we are talking about the flip flops. So, mm, one circuit is given like okay, we have a D flip flop. This is the Q naught, D naught. We have a D1, Q1, Q1 bar. I am using one NOR gate. Sorry, one OR gate to define a final output. This is the X. Q1. We are using as a D naught. Similarly, it is a X bar. With the Q naught bar. Q1 bar. Okay, I am giving this circuit. And that particularly is connected to D. The clock signal is the common. The clock signal is common. Now you have to calculate Q naught, Q1, after 3 clock pulse if initial Q0 Q1 is 0 1. This is the one type question of related to the flip flop. Okay, and assume applied input x is 1 0 1 1 0 1. It should be 1 1 0 1 0 1. Okay, so we assume that at clock 0 Q0 Q1 Q0 Q1, we assume the x also and y also, and yeah. With respect to this, we define a d naught d1 also. X d naught d1 q naught q1 and y. So at clock 0, we only know what is the q naught q1. Remaining thing we don't know. Okay. Now when we apply the clock 1, before that one, if q naught is 0, so q naught bar is 1. Okay. So here we are getting 1. Okay. If q1 is 1, so q1 bar is 0. So 1 0 and x is also 1. X is also 1. So it is 0. So at d naught, d1 we apply the 0. Okay. X is 1 and second it is a q1. So q1 is 1. So we are getting a 1 here. So d naught is 1 and d1 is 0. Okay. Now if d naught is 1, so what is the q naught? Q naught is 1. And what is the d1? It is a 0. Okay. Now if q naught is 1 and d naught is 0 but d naught bar is 1, so 1 and 1, so output is 1. Now apply the clock second. Now if q naught is 1, so q naught bar is 0, so this one is the 0. If q1 is 0, so q1 bar is 1, so we are getting 1 here. Okay, and x is what? 1, so x bar is 0. So again d1 is 0. Okay, and what about d naught? X is 1 and q1 is 0, so it is 0. So again d naught is also 0, so it becomes a 0 and 0. If both are 0 0, so what is the output? Q1 bar is 1, so 1 and this one is the 0. We are getting a 1 as output. Now clock 3, x is 0. Okay, q1 bar is 1 because q1 is 0, so q1 bar is 1. Q naught is 0, so q naught bar is also 1. And x is 0, so x naught bar is also 1. So d1 is 1. Okay. Similarly, d naught, X is 0, so this is the 0. If D naught is 0, Q naught is 0. If D1 is 1, Q1 is 1. Okay. Now Q1 is 1, so Q1 bar is 0. So we are getting a 0 from here, we are getting a 0 from here, so output Y is 0. Clear? So what is the output after 3 clock pulse? 0, 1. So this is the one question. Question 1, output in terms of Q naught Q1. So that is 0, 1. Question 2, the output in terms of Q naught Q1 by output Y. So that is a 0, 1 oblique 0. Question 3, state diagram. Okay, so state diagram, I just start the state diagram. So we, as we know that we have a two outputs D naught D1. So with respect to this one, we are getting a 4 state: 0, 0, 0, 1, 1, 1, and 1, 0. Okay, any in any sequence you can write. It is not up to the condition that you can write in this way. You can write in any form. Okay, now if clock 0, this is the 0, 1 state. 0, 1 state. Okay, now with respect to 0, 1, what is the next state is the 1, 0. So we are going, next state is the 1, 0. For this one, for going this state to this state, what is the input? Input is 1 and output is 1. So we put a input as well as the output. Okay, now with 1, 0, we are going to the 0, 0. So we are going to the 0, 0. Okay, now in this case, what is the input? Input is 1 and output is 1. So we mark as a 1 and 1. Okay, with 0, 0, we are getting again a 0, 1. 0, 1. But in this case, what is the input? Input is 0 and output is 0. Okay, if we write a more state, so we can basically combine these particularly all state, and this is my flow diagram or state diagram. Okay, just any doubt? Any doubts? No doubts. Then shall we close the meeting?
No, sir. I have a doubt in week 12.
Mm-hmm.
Practice assignment 12, question number 12.
Practice assignment 12, question number 12. Yes.
So the accepted answer is 12.5,
Mm-hmm.
but my answer is coming up to 12.99.
Okay.
Yeah, so can you like, is
Mm-hmm.
there a mistake or like,
A pipeline system shown below has a D flip-flop with T setup 2 TCQ 5 nanosecond and a combination of blocks CB1, CB2, CB3, CB4, LSTPD1, 30, 40, 39, 29, 40, and 25. Okay, so these are taking the 7 nanosecond. Okay, so we are getting an output here at a 7 nanosecond. So this is my state. Here we are getting the output at a 7 nanosecond. Now, after that, we are getting an output after 37 nanoseconds here. Okay, we are getting an output after here as a 20, 66 nanosecond and 77 nanoseconds. After that, we go to this one. It will be take as a 84 nanosecond. Okay, and 66 or 7. Here we are getting a 73 nanosecond. Okay. Finally, we are getting an output here. .98 nanosecond. Sorry, 109 nanosecond. And here we are getting as a 116 nanosecond. Okay, so it is a t is equal to 116 nanosecond, as is what 10 raised to power 9 divided by 116. So it is 1000 divided by 116 into 10 raised to power 6.
It's 8.62.
8.62. Now what they are asking a question.
So shouldn't we just consider the critical path and then add the clock and the CQ and the setup time after finding the critical path?
Hmm. Basically, you are getting the output when you are getting this one. Okay.
Yeah, like yeah, you can.
So
I think you're calculating the output delay.
yeah.
Yeah, but they need the clock frequency, so I think we need to find the clock period, right?
Yes. The question is clock frequency that system can operate is. So setup time is 2 nanosecond and TCQ is 5 nanosecond. So which critical path you are selecting here? Hmm, 1, 2. Yes, which critical path you are selecting?
So I was going to CB1, then CB3. So that comes to 70 nanoseconds.
CB1 then CB3. Okay.
CB4 is independent, so we can rule that out. It's just 25 nanoseconds. And the other one is CB1 to CB2, which comes to be 59 nanoseconds.
Yeah. So when we start from here, so here to here it will be take a 59 nanosecond. Okay, from CB1 to CB2 we are taking a 59 nanosecond. Whereas CB1 to CB3, we are taking a 70 nanosecond.
Yes.
Okay. Now CB4,
CB4 is just 25.
mhm. So 70 plus 25. Mm. So how we calculate?
Shouldn't we just stop at the 70 since it's going to the another flip flop that will take the output at the next clock cycle, so the maximum propagation delay is till CB3, right?
Yeah, CB1 to CB3.
Yeah,
That is a
so
70.
yeah,
Okay.
so 70 plus 7, 77.
Mhm.
Yeah, so it comes to
So if we are taking 1000 divided by 77, so it's a 12.8.
yeah, about 12.99.
Mm, it is a range or basically the 12.5 is the final answer.
Or it's the final answer. There's no range.
Mhm.
If you take critical path delay to be 80 nanoseconds, then it comes to 12.5.
12.5.
Yeah.
And
So,
30, 40, 70. Mhm. I think, okay, the answer is incorrect. So I think it should be the range 12.5 to 13.5. I think so. I have to check that one.
okay.
Okay, I don't have this particularly. Maybe it will be the range, but the yes, answer is correct. It is at 12,000 upon 77 megahertz.
Okay.
So 12.98.
And also, if we like calculating the output delay, right? So
Hmm.
for that, we will only count the TCQ, right? Not the T setup.
T setup, we are not counting the T setup all the times, but we have to count the T setup first time.
Or we have to do it for the first time.
Yeah, because
Okay.
first clock pulse is applied. Okay.
Oh, yeah. Yeah, yeah, yeah.
So we have to count at a first time, but not every time.
Okay. So my next question is from the graded assignment from the same week. Question number 2.
Mhm. Yes. After the clock arrive at D flip flop. Okay. What is the earliest time the output Y guaranteed to be valid and stable? Okay, so if you see that Y output will be dependent on two particularly data. Okay,
Okay.
one data that is coming from this way, from the second flip flop, with two NOT gate, one AND gate. Okay, one data that is coming from here, and similarly the data will be going as the input for D2. So flip flop is the 4 nanosecond. Okay, so the 4 for 8 nanosecond, you are getting a Q1. Eight,
For this, they are asking
seven, yes,
for this question, they are asking after the clock edge.
yes, after the clock is. So 4, 5, 6 to 8, 8 of 4, 12. Okay, 2, 9, okay. Okay, so when your Q1 is arrived,
It arrives after 4 nanoseconds.
yeah. So, so if this flip flop will be taking the 4 nanosecond delay, okay, so it is a 4 nanosecond, 4 nanosecond, 4 nanosecond, 1, 1, 2, and 3 nanosecond. Okay, so 4 nanoseconds you are getting output at a 4 nanosecond. B apply individually. So after 4 nanosecond you are getting the output. 5, 6 nanosecond you are getting here output here. Okay, so after 6 nanosecond you are getting a 2 nanosecond delay. So it you are getting a 8 nanosecond here. Okay, and from 8 you are getting a 12 nanosecond here, 11 nanosecond here.
Sir, won't the output of U2 goes into D2, right? And Q2 appears after 4 additional nanoseconds. So the other input of U3 comes at 12 nanoseconds. Won't it add up?
Oh, it is a 8 nanosecond that will be going to the this one. Yeah, so the input is appear at a 8 nanosecond.
Yes, sir. And then Q2 will appear after 12.
12 and 3, 15 nanoseconds. So this is the 15.
Yeah, I actually got 15 nanoseconds.
Yeah, it is definitely the 15 nanosecond.
Okay. But after that, I was thinking it for the other way, like how to get 11 nanoseconds.
Mm-hmm.
Like this is a Moore machine, right?
Yeah.
The output doesn't depend on the input. So they're asking after the clock edge, right? So when U2 arrives at D2,
Mm-hmm.
at the first clock edge, it's invalid for 8 nanoseconds.
Uh-huh.
D2 then D2 is valid, and then Q2 at the next clock edge, Q2 appears. So at the second clock edge, Y appears after 11 nanoseconds. If we don't count the first, I actually drew a timing diagram of this. Can I share my screen?
Mm-hmm. Sure.
Yeah, I just need to join in from my tab.
Okay. But the thing is that they are asking the valid output. So you are getting the valid output when you are applying the D2. And you are getting the D2 after 8 nanoseconds. So
Yeah,
that means your valid output will be taking as a 12 nanosecond.
okay. I
If I am not asking about the valid question, it is mentioned that it is a valid. If not, I am not asking about the valid, so I can take at 11 nanosecond is the output. Mhm.
okay. Can I share my screen for a
Yeah,
moment?
sure, sure.
Okay, so yeah, so this is the timing diagram I tried to draw.
Uh-huh.
So I assumed A and B like random inputs.
Mhm. Mhm.
So I found Q0 and Q1 to be valid at the first clock edge, right? Because
Yes.
it's just A and B, right? So
Mhm.
and Q0 and Q1 appears after. So this is my TCQ, and
Mhm.
this is the delay of the logic gate U2.
Mhm.
So
Mhm.
in total, this total is 8 nanoseconds, right?
Why
But
it is 8 nanosecond?
because for the NOT gates, two NOT gates, and the AND gate, it comes
We
out
are
to
getting the
be because hold on here. So this is one, four,
yeah,
four, four, 6. So this is 8,
yes 8.
right? Yeah. So it's
Yeah.
adding the TCQ also,
Mm.
and but D2 is invalid for 8 nanoseconds because it's
Yeah,
taking its
D2 is
output
invalid
from
for
later.
8 nanosecond.
Yeah. Okay, so if D2 is invalid for the sampling edge, Q2 is also invalid for the whole clock, whole
Mhm.
pulse.
Mhm.
This one, and after that, Q2 appears. It will sample D2
Mhm.
after TCQ 4 nanoseconds. So this is also 4 nanoseconds.
So
So
8 you have already considered, then 4 again you are taking.
yeah, so this is at the next clock edge.
Okay, next focus.
So D2 will appear over here. So this is D2, which will appear at Q2. And now y is invalid for the whole first clock because Q2 is invalid because it's taking input from the Q2, right? And also it's going to be invalid for the TCQ time because Q2 hasn't settled yet for the next clock edge.
Okay.
So this is also for, I've written it over here. And then y, so this time is Q0, Q1. This is the next clock for Q1, for Q0 and Q1, right? So this is the next value of Q0 and Q1. So y is basically doing, it's ORing the previous value of Q0 and Q1 and the current value of Q1 and Q0 and Q1. Like that's what I assumed from the machine.
No.
Like, isn't it like doing the same thing because U2 is getting delayed for 4 nanoseconds, right? From the third flip flop. So yeah, so then I did the 3 nanosecond for the XOR gate. And so this 4 plus 4 plus 3, this comes out to be 11 total. So that's how I got 11 nanoseconds, but I don't know if I'm right or not.
No, we are not. We are taking the, like for example, we are taking the clock first. Okay, that is okay. Okay,
Yeah.
but till 8 nanosecond, you are not getting the output input
Yes.
D2.
Yes.
Okay, so if
Yes.
you are not getting the input till 8 nanoseconds, so how you will be getting the output at same time 8 nanoseconds? If we apply the clock at the same time also,
No.
okay,
So
if we apply
yeah,
the
yeah.
clock at the same time also, like for example, what is the setup time that is required? In the question, the setup time is 3 nanosecond.
Yeah.
369.
Yes. The setup time is 3. So I'm counting 3 nanoseconds also for the setup time, but it's not affecting the delay of the output. It's just going to affect the clock frequency.
Yeah, it is affected the clock frequency.
Yeah.
So if I am taking the first clock will be applied at a start from the 0.
Yeah.
Okay, taken with 3 seconds to the setup, then again it will be going to high and it will be a 4-second clock.
Yes.
So it becomes 7. 11. 14.
In the first clock edge, in the first clock cycle, D2 will appear after 8 nanoseconds because it's coming from the output of the first 2 flip flops. So D2 will appear immediately,
Yeah,
but Q2 will appear at the next clock edge because it's a D flip flop output.
yeah.
So it will appear after the second clock edge, and then Y will compute its valid output, not at the first edge.
So you are getting the 8. Wait a minute. In the question, what is it is given? Okay, so basically the thing is that T setup and T CQ, it is given with respect to the clock signal, not with respect to the flip flop.
Okay.
Okay. So if you apply a input here, so you are not getting a 4 second here. You are getting exactly the same time. That is the, if I am to apply the at a 1 second, so you are getting a output 1 second here. You are getting the output 1 second here. Then 2 second here, 3 second here, 1 second here. Okay. Now you are getting output at a 3 second. Okay. One output you are getting after 3 nanoseconds.
Yeah.
Okay.
From
But
the XOR.
you are, this particularly you are getting at a 3 nanosecond. Okay. You are getting an input D2 at a 3 nanosecond.
Okay.
But your clock will be applied after 8 nanoseconds. Because it is a 4 ns. It is a 4 ns. So again your clock pulse will be applied the 8 nanosecond at this point. You are considering this is the your first nanosecond. So you are getting a clock pulse at an 8 nanosecond.
But we do calculate the clock pulse in the fourth question, and it comes out to be 14 nanoseconds. The clock period. Like, yeah, the fourth question asks the same question, like what will be the frequency. So
Fourth question. The maximum clock frequency that the system can operate is.
yeah, for that it's 14 nanoseconds, and yeah, that answer is correct.
It is a 14 nanosecond.
Yeah, for the clock period.
Okay. Uh, but you are getting 15 nanosecond, not a 14.
Yeah, for the output delay, I'm getting 15 nanoseconds.
But the
But
clock,
yeah, but from this timing diagram, it comes out to be 11 nanoseconds, and I don't know if this timing diagram is right or wrong.
the timing diagram is, if
Because
we
if
say
this
that,
is correct, then the right answer might be 11.
yeah. Now, okay. The thing is that when we go to the question number 2, initially we start with the question number 2. Okay. It is
Okay.
saying that the setup time and the clock time period is a 4. Setup time is 3 and clock time is a 4 nanosecond.
Yes.
Okay. But it is saying that input is applied at a edge of the clock. So that means input is applied at this point. So we don't consider the setup time.
Okay.
So like this is my clock. Okay. If I say that it is a start from 0, then 3, then for 4 nanosecond it is on, then 4 nanosecond it is off, then 4 nanosecond it is on, then 4 nanosecond it is off. Okay.
Okay.
Clear? Now the thing is that when we apply the input as a clock edge, so automatically it, without any delay, it will be getting as a output. So like for example, if 3 nanosecond I apply the input, okay, we are getting a same 3 nanosecond as the output. Similarly, if 3 nanosecond we
But
apply the B, we are getting the same time as the output.
won't we consider the TCQ time?
TCQ time is not considered for that one, na? Wait a minute, I just tell you. It is not a flip-flop delay. It is a clock's TCQ.
Yeah, the time it takes from the clock's edge to appear at the output, right?
Hmm.
For the data to appear at the output. That's TCQ. Because in the lecture, professor said like for every flip-flop you add to the pipelining system, it will increase your latency because TCQ adds up. I think it was in lecture number. Yeah, it's in maximum operating frequency. He didn't say anything about T setup. He only said like TCQ will keep
Yeah,
adding up.
yeah, TCQ is the delay. So we are getting a 7 nanosecond here. We are getting a 7 nanosecond here. Okay.
Yeah.
If we apply the input at a, so 7 nanosecond, we are getting output. So here we are getting at a 7 nanosecond. Here we are getting as 8, 9, and here we are getting at 11. Okay.
Yes.
Again at 11 nanosecond, when you apply the input, we are getting output at a 15 nanosecond because of TCQ.
Yes. Yes.
Okay. So 11 nanosecond here, 15 nanosecond here, 3 nanosecond it will be provided to me. So total is the 18 nanosecond. Okay. Now we
Yeah.
start with the 3 nanosecond, we are getting 18 nanosecond. We assume that it is the starting point. 3 nanosecond is the starting point.
Yes.
So we are getting a 15 nanosecond delay.
Yes. So I think the question is a bit ambiguous because it doesn't say like at which edge you need to calculate it. Because this total time
No,
is for the first clock edge.
as is defined from the basically clock signal, basically clock representation.
No, is it like at the first or at the second? Because the third flip flop comes into play at the second clock edge.
Yeah, third flip flop will come at a second.
Yeah. So, I mean, if you count from the second clock edge, the answer is different. If you count from the first clock edge, the answer is different.
Yes, exactly. If you count at a second clock edge, the answer is 15. If you count as a first clock edge, the answer is 11.
Yeah.
No, 11, 14. No, wait a minute. The answer is 8 and 3, 11. Yeah, 11 nanosecond.
Yeah, 11. Yes. But question doesn't specify like it just says after the clock edge arrives at the D flip flop. So I assume it was the first clock edge.
But if it is a first clock edge, your output input is not a valid now at a first clock edge. You can't say that your input is a valid input at that situation.
So we'll count from the second clock edge.
Yeah, we count from the second clock edge because
Okay.
you are getting the input after 8 nanosecond, and
Okay.
after 8 nanosecond is automatically the second clock edge, because if you see in the diagram.
Okay, so then 11 is correct. Yeah.
No, second clock edge, then 15 is correct. For the first clock edge, 11 is correct. For the second clock edge, 15 is correct.
Wait, how?
8,
Shouldn't the time be increasing? Like,
12, and 315. Yes, if you consider the second clock edge, so 4 TCQ is increases, na?
okay. So it should be 15.
Yeah, it should be 15.
Okay, so hmm, yeah, this is kind of like really confusing question. I was like,
Actually, we have not checked the answer. This TCQ clock. Oh, nanosecond. Okay. And if we consider the first cycle, the answer is 11 nanoseconds.
okay, so but at the first edge, it's not valid, right?
It's not a valid.
So we'll have to consider the second one.
Mhm. After the clock has arrived and before what is the earliest time, the output Y is guaranteed to be valid and stable. And even though we don't know the clock frequency, so we can't identify that what is the time period of the clock signal. And the critical path and the delay is the U0, U1, U2, and then U3. 1, 2 to 4 or 3, 7. 4, 4, 8. Yes. Any other doubts?
No, so that's all.
Okay.
Thank you.
Thank you.